Okay, everyone, so I just want to remind you that you can pick your exams up at 23 Illini Hall any day 4 to 6 p.m. if you didn't already pick them up in class. And something very unusual happened this time for the first, okay, so your exam average as a whole class was, I think it was 86 with a median of 89. And in Stat 100, when I'd been looking at the online versus the in-person section, which we did all last year in all 8 exams, the online people scored higher. Sometimes it wasn't significant, but it was always higher. But here it was the in-class people scored 3 points higher on the average. So your average was 3 points higher than the other one, even though the overall was an 86. So yours was, I can't remember exactly, but something like an 87.5 versus an 84.5. Not exactly sure why that is. So we've got, the story's going to be kind of complicated, but overall, online people and in-class people are doing, are doing very well. It's just, I was surprised to see that. So who knows why. So there's some ideas I have, so we'll be looking at that later on in the semester and see if it holds up for the next exam. Interesting. All right, so now, we left off last time talking about seeing that we could do both. We had these 4 statistics to basically test the same thing on the bottom on page 51. And we said that the Z and T statistics can give you either a one-tail or two-tail test, meaning if you look at the statistic, it can be positive or negative. Whereas the chi-squared and F don't distinguish between positive and negative. They're squared statistics, and they're the statistics that they're going to be the only ones we can use when we start adding more predictor variables. Right now, in chapter 11 here, we just had one X predicting one Y. Starting today, we're going to look at more X's, more predictor variables. And then these will be the statistics that we'll have to use to look at the overall regression effect. Because when you have multiple slopes, some of them could be positive, some could be negative. You can't just boil it down to a single signed difference between 2 numbers. So you want to look at the whole pattern, and the way we do that is by the squared differences. So basically, as you saw, these are the squared. For the simple regression, when you just have one predictor variable, these are the same, except this will always give you, the two-tailed version of this. And same with these. Okay? But now, if we go into multiple regression and we'll look at the overall regression effect, what's in our model, and we have whether our model does assess the fit of our model when it has more than just one predictor, we're going to have to be using these. Okay? We're not leaving these behind because we can look at these for individual slopes. But for now, for the overall regression, we're going to have to stick with these. So just the F was new to everybody here from a show of hands. So I realized that you should probably look at, you should definitely read this on your own, and maybe we should just highlight some points here. All right, so as you saw, this F statistic, or the F ratio, is a ratio of basically the strength of your model, the mean square model, divided by the mean square error. And what it's used for is to test the null hypothesis of no effect in linear models, and not only in regression models, but when we do something, when we're comparing more than 2 means. When you compare 2 means, you can do a 2-sample Z or T test, but when you have 3 means, again, you can't boil it down to a single sign difference. You have to look at the whole pattern, and you do an F test. Okay? And we want to know whether, okay, so what do you need to know here? Basically what we're doing here is we're breaking up, we're using analysis of variance. So we're breaking up, we're trying to predict a Y variable, some Y, and we have model, right? Signal and noise, model and error. And we're doing this when we have when we have a linear function of the x's. So the main idea is you break up this variance into two parts, right? The variance explained by the model and the variance missed by the model, and this left in the errors. So that's basically what we're doing. And the null hypothesis is that the model does no better than chance. Knowing the x variables tells you nothing about y. You might as well just predict the average y. It's not going to do any better than that when you're testing the overall regression effect. And so then is usually what do? We say, okay, so we assume this null, that whatever effect you see that is just due to random variation, right? We just have, the idea is that we don't see the entire population, we just see some sample, and we're trying to make a prediction, or we're trying to understand what's happening in the whole population from just a sample. And so we assume this null hypothesis that nothing's going on, it's just chance variation, and then we look at the sampling distribution of some test statistic, in this case it's the F statistic, under the null. And if it's far enough away from what we'd expect, if the chance that we'd see such an extreme value from what we'd expect, just under chance variation, if that's chance is really small, called the p-value, then we reject that and we say that there's some meaning to our model, there's some significance, that there's some particular reason for it rather than just the luck of the draw, right? And that's the idea. And but looking at the F distribution is our hardest distribution to look at, as probably some of you found out, because there's lots of different F curves, and they depend on two sets of degrees of freedom. One that's degrees of freedom 1 are for the numerator, and that is associated with the model, and it's the number of parameters in the model, including the intercept. So it's just the number, if you have a model that has 2 predictor variables, so far we've only had 1 predictor variable and an intercept. So the number of parameters is 2, and it's always the number of parameters minus 1. Basically, it's the number of your predictor variables minus the intercept. So it's, if you have 2 x's predicting a y, like we're going to be looking at, then it would just be 2. If you have 3 x's predicting y, 3 x predictor variables, if you have if you want to predict your final scores based on your homework, that would be 1 predictor variable. Maybe on your attendance, that could be another one, and maybe on, I don't know, how much you study. That would be 3 predictor variables, and you'd also have an intercept, 4 parameters, but your degrees of freedom would be just 3, because you have 3 predictors. And then the degrees of freedom for the denominator is based on your sample size. And this is where it's similar to the t distribution. It's based on your sample size. But it's the sample size minus each parameter that you're estimating. So if we have those 3 predictor variables and 1 intercept, it would be n minus p, n minus 4. Your sample size minus every predictor variable plus your intercept. So that's why it is. So it's much easier to use the p-value calculator because it makes those tables many pages long. But unfortunately, on the exam, you can't use your p-value calculator, so you have to learn how to use the tables as well. And that's what you learned last time. And then just this idea, you should also read this. I'm reading it with you because we're a little bit ahead of the game. We weren't supposed to finish this chapter like we did last time, but we went quickly, I guess. So this basic idea of hypothesis tests, it might be useful to read together, is that all these hypothesis tests or significance tests are statistical checks to determine whether some effect you see is due to some particular cause or whether it's just due to chance. That's what we talked about. And usually the numerator of the test statistic is a measure of how large the effect is, whether the strength of your model, right? The strength, how large your effect is. And the denominator is a measure of how large the chance error is. And so far we've looked at 2 basic situations. We've we've used z and t-tests for the situation what? Where you can boil things down to a single difference. The effect can be your observed minus your, like your observed slope minus your expected slope, or your observed average minus your expected average. And you can boil it down to either a single signed number. These can be positive or negative. But these chi-square and f-tests cannot be expressed as a single number with a sign. Instead, we're looking at a whole pattern of differences, and we want to know if the whole pattern differs from what we'd expect under the null. So in these cases, we square a set of differences and combine them so that the positive and negatives don't cancel each other out. So these chi-square and f's can never be negative. They're squares, so they're always positive. All right? So we did something a little bit unusual. Usually people don't introduce these tests until you hit multiple regression, but I wanted to show you that for simple regression, we can just always square the z and the t-test to make them chi-square and f-tests. But in our next section, what we're going to be doing now, in sections 4 and 5, and from now on out, we won't be able to use them because we'll have multiple slopes that could be positive or negative. They could cancel each other out. We can't just, there's no way to just come up with a single number. So we have to use these chi-squared and f-tests. All right, and this is true of all the significance tests, okay? All the significance tests, the bigger the test statistic in absolute value, the bigger it is in absolute value, the farther away it is from 0, the more significance you have, the smaller your p-value, and the more evidence you have to say, hey, it's not just due to chance. We have some effect here. Because all these null hypotheses, all these test statistics are looking at a distribution and assuming that any deviation from what you'd expect to get is just due to random variation. So the bigger your test stat, the bigger your f is, the bigger your chi-square is, the bigger your z, t, all of them, the farther away it is from what you have more significance and you have more evidence to reject the null. Okay, and so there's two things that influence the size of the test statistic. And one is the size of your observed effect, just how far your sample landed from what you'd expect. And the other one is your sample size, right? Your sample size. Like you can just look at that. The more sample size you have, the more significant your effect is. And that's why I like this form of it, where you can see that this right here is your effect size, this R, the correlation, and the multiple correlation coefficient, and then the bigger your n is, you can see in all of these that's the bigger your test statistic. I mean, I simplified this. This n is part of the degrees of freedom in the denominators here, but when you simplify it, it's a nice simplification because you can just see that the bigger your sample size, the stronger evidence you have for some effect. So that's the idea. So now what are we going to do? Now we're going to, and there was we're going to start multiple regression. And I thought we might as well just look at it, start at a problem we already did back on page 21. We looked at, remember how I said that one of the main reasons people use multiple regression for a lot of reasons, but one of the main reasons is to control for a possible confounder. You put what's called a covariate in the model to control for it. And I said that when we looked at this back on page, this was from our data that shows that the bigger your foot size, the fewer shoes people buy. And so this is the same example that we saw as on page 21. So this is same as page 21. This is right here. If you want to look back at it, we can. Let's look back at it. So this was the same as page 21, same exact data set. And back there, we saw that this was an example where we had this confounding. This overall regression was misleading. You really had females up here, males down here, and if you split the data, we said if you split the data, it would balance out. It would balance out. And we said there's two ways to control for confounder. The first way is stratification. That's what we did here. But there's another way that we can do it. Where did I say that? Stratification, and I also said modeling was the other way we can do it. Sorry if I can't find that right here. Oh, right here. Stratification and modeling, including the confounder as an independent variable in a regression model. So in part 4, we're going to look at the same example, and that's what we're going to do, both by stratification and modeling, so I can show you how that works. So let's do it. So we're going to do that. All right, here. Okay. So this is our Stat 100 survey data. And the idea was what? That we have, that maybe we should just look at it. Why don't we just go and look at it, and you can see this data, and you can see what we're doing. So let's go to the PC. And here it's spring, this is the data set. And we're going to look at a scatter plot here. And our Y variable is the size of the student's feet, and this is how many shoes they buy. And it's exactly what you have in your notebook on page 71 here. And this is the regression line, and we got this regression equation and a fairly strong correlation coefficient of negative 0.3289. And basically it says for each extra pair of shoes, the slope in front of the shoe size says that for each extra pair of shoes you own, you typically, on the average, buy about 2 fewer pairs of shoes, 2.154. All right? So that's what we had, and we said, why would that be? That doesn't make sense. And we said, well, maybe it's confounded by group membership, by gender. So we thought, okay, let's split on gender. And we did, and we said, yeah, sure enough, it goes away. So if we look at stratify on gender split, we see that if we just look at the males, and you look at the equation here, there's essentially no slope. So it says for each extra pair of shoes that guys own, it's basically no slope at all. It's just 0.09. It's very flat here. And for females, it's pretty much no slope. It's very small effect, 0.34, and it's not significant. So it's basically, it disappears. And we said, okay, what's going on here? So we said, when we combine the plots, you can see that basically the purple is girls. There's a lot more girls in the class, and they tend to have more shoes and smaller feet, and the boys are the yellow right here. And these are the regression lines, and and that's the idea. And first, what we're going to do is we're going to show that if we include gender as a variable, we'll get something very similar to this, but we'll get equal slopes here. That's what we're going to do first, which isn't very far off here because they're very close to equal, and that's what we're going to do first. All right, so let's do that. And let's go back here. So what am I saying here? I'm saying that basically, if you want to see what's going on here, I'm saying that this overall slope is misleading. When you stratify into males here, these are your males and these are your females, that effect goes away. And we saw that was because the confounder, there's a third variable here that's driving both the shoe size, the number of pairs of shoes, which is your Y, the number of shoes, and the shoe size. And that's gender. And a good visual to remember, an extreme visual, is this. That on this plot, course, there's overlap between boys and girls, but the idea is this, that you have the girls up here, a group of girls up here. These are the females. And then you have a bunch of guys down here. These are the males. This is shoe size. They have big feet. So this is the shoe size. They have bigger feet, and they buy fewer shoes. This is the number of shoes. So when you try to fit a line through them, you get this misleading negative slope, even though within the girls and the boys, there's no slope. So this is a confounder because group membership happened first, and it looks like it's that's what's driving it. It has nothing to do with the size of one's feet. So that's the idea here. So all right. Now we're going to look at how including gender, this is what we're going to be doing right now. You see how it looks when you stratify. Well, we're going to show you how we can also just make a single, instead of having two separate stratifying like this, we can include gender as a predictor variable along with the shoe size and a multiple regression, and that will do a very similar thing as this. It's going to do something, all right? But first, what does it even mean to include this? Gender is just a yes, no, binary variable. You're male or female. And what does that even mean to do a regression with a predictor variable that's binary? So just because you might not have ever thought of that or thought you could do that, let's see what that looks like. So we can see what that looks like. Let's just go over to where I got this from, and you can see what happens when we do that. So let's go back to the computer program. So now what are we going to do? So now we want to just instead of doing shoe size predicting shoe number, why don't we see what happens if we do gender predicting shoe number? Gender, and what does this even mean, 0 and 1? Well, for a binary variable, you can code it as 0 or 1. So I coded males as 0 and females as 1. So basically you can think of it as, okay, that's just how you code binary variables. You code them as 0 or 1. Yes, no, all right? And so what this is doing is it's right here, it's just saying, all right, all the men are right here. There aren't as many of them. One of them does own 80 pairs of shoes almost. But what do you think this is right here? It gives you this regression equation. It says the shoe number is equal to 6.884 plus 12.86 times gender, and there's this correlation of 0.5. What is this 12.86 times? This is a slope. So just because I coded men as 0, I say as you go from over 1 all the way to females, you're going to have a difference of 12.86. You're going to go up. What do you think this point is right here, this 6.884? What do you think that is? What do you think? Do you know what that would be? What do you think? It is an intercept, but because it's an intercept, when your x variable, gender, is equal to 0. But when your x variable is equal to 0, that means you're male, right? When your gender is equal to 0, that means you're male, so you're right here. So what do you think that 6.884 is for males? It's their average. It's the average for men right there. And then what do you think, then it says, what do you think this 12.86 is? You go over 12.86, you add 12.86, and then up here you get the average for females. Does that make sense? I mean, if we split this according to gender, we'd get shoe number. There's the average for males and the average for females. Okay? So let's look back. And so that's all we're doing here. I mean, if you wanted to look at their averages, you could look at box plots or histograms for the shoe size, and you could split them. And let's see if we could do a box plot even, and side by side. All right, so here you could probably see, let's look at our statistics. So there's the median, so there's our average for, oh, what did they do? They must have coded males, they didn't code them as, oh, this is shoe size, sorry. I want shoe number, very sorry, I apologize. I want shoe number. Okay, so this is what we're looking at, the shoe number. So let's look at the statistics here. And there's our average right there. And so that's what the regression is predicting. Okay? So let's go back home to our scatter plot. And we're predicting gender and shoe number. All right. Now what would have happened? What do you think would happen if I switch the coding? It's arbitrary. What if I coded females as 0 and males as 1? How would that change? Let's think about it. That's one of the questions I ask in our notebook. So let's go back to our notebook and look at this. Okay, so here's our equation right here. So right here, I said y bar, which is the average for guys, is 6.884. That's the average number of shoes. And for women, we know they buy more shoes, so it's much higher. All right, and there's the regression equation we saw right here. Okay, and remember, we coded males are equal to 0 for x here, and females are equal to 1. So what does the regression equation give for males? For males, it gives what? That our best prediction for males is 6.884 plus 12.86, and males are coded as 0 for x here, times 0. So that's just what our best prediction is, just the average. Okay? So that's just equal to the average for men. And now let's do the same thing for females. So we have, for females, what does it give? So it's 6.884 plus 12.86. And now x for females is not 0, it's 1. So here we get 19.74, which is the average for females. So let's put, that's right there. Okay. So now I said, what if we coded females as 0? What if we switched it? What would the regression equation be? Well, what are we doing here? Maybe it will help if we looked here. Do you see what we're doing here? Because males are 0, we're thinking, okay, since males are coded as 0, when that's 0, let's just put in the average for males here. That's what we're doing. That's the average for males. And then what's this 12.86? When females are 1, well, that's just going to be the difference. When we go from males to females, we have to add 12.86. So that's just the female average minus the male average. So that's the form of it. So now if we switch the coding, think what we would do. If we switch the coding and all of a sudden we coded it as females as 0, what would we do? Females would be down here. So we take this bar, they're now 0, and put it over here, and their average is like right there. And picture this vertical strip, we put it at 1, and do you see how this line would just, instead of going this direction, it would just be the same difference, it would just slope down like that, right? So that's all it would be. And so we'd have a predicted value of, we just switch it, 19.74 plus instead of, so it would be the female average, and there would just be a minus there, right? It would just be the difference. You could say plus 6.84 for minus 19.74x. So it would be just 19.74 minus 12.86x. Right? So that's all we do. It would just be the opposite slope. So that's just a binary variable, 0, 1. And it's also called a factor variable, a categorical variable with just, in this case, it just has 2 categories, but we really do the same thing if we add another category to it. You just code, you can code them as all 0, 1 variables. All right, so now let's go to our next page. And so now what we're going to do is we have basically these 2 simple regression equations. One says, okay, based on your gender, there's this giant difference, this giant slope, 12.86. If you're a female, you're going to have, on the average, 12.86 more shoes than if you're a male. That's a giant slope there. And then we have this other little effect that's just this effect here. It's not so little, it's this one right here. It's this confounded one. It looks really big, but it's going to disappear. Once we put gender in, this slope of negative 2 point something is just going to disappear. And I will show you how that works. Okay, so now what are we going to do? So let's combine them into one multiple regression. All right, and this serves almost the same purpose as drawing 2 separate scatter plots as stratification, almost. It allows us to separate out the effects of how much of the effect we see, how much of this effect we see is really just due to the gender, and how much is left, how much is due to shoe size and how much is due to gender. Okay? So the multiple regression, we have one binary categorical variable and one, okay, so this is multiple regression. Now we have 2 predictor variables. We have an x1, see, we have an x1, that's for gender. And then we also have, we're going to have 2 variables. We have, this is the first time we're doing this. And then we have an x2, and that's going to be shoe size. All right? And so here we're going to say that the shoe number is some intercept plus the effect due to gender here plus the effect due to shoe size. And we predict that this shoe size is going to almost disappear. It was pretty big here, but it's almost going to disappear. All right. So what this does, what multiple regression does, and this is very important, is that the slope of each of the x's in the model controls, another use of the word control, controls for the other variable. What does that mean? It means, like, for example, the slope for gender. It says it estimates the difference that gender makes in predicting shoes for those with the same shoe size. So, for example, looking at people with the same shoe size, say size 10. So you look at, some of them are women, like I have a size 10, most of them are men, but we want to see how much of a difference gender makes. So shoe size is out of the picture. Everybody has the same size shoe. This is what it says. Now, how much difference is left just due to gender? Okay? And then you also get, this is what multiple regression does. It controls for all the other variables in the model. So the slope for the shoe size, what does that do? It estimates how much an increase in shoe size, going from like a 10 to an 11, affects the predicted number of shoes, affects how many shoes people own for people of the same gender. So you would just compare like females size 10 to, when they go up a shoe size to 11, to females, within, size 10 to size 11 within each group, keeping the other one the same. So that's what multiple regression does. All right. Now, so now we're going to, now we have 2 variables, so we can't just draw it in the plane. We're going to be in 3D here. So, and we have to do, we can't look at a z or a t statistic. We have to look at this analysis of variance. All right, so here's our analysis of variance results. Let's just look at them here first. And what do we get? So now we have these three parameters, the intercept, the slope in front of gender, and the slope in front of shoe size that we're estimating here. So these are our three parameters right here. And they're called slopes, even though this one's really an estimate of the intercept right there. Okay? For some reason, this program just spit out saying that they're all slopes. So these are the three parameters. So P is equal to 3. Now you have an ANOVA table here. Remember, P is 3, and N is what? P equals, so you can just look at this, P is 3, and N, there was 1,046 students in this data set, in this survey. So you can see that this is N minus 1, right? And this right here is the number of predictor variables. You see, minus the intercept, so it's P minus 1, 3 minus 1. And this is N minus P, just like we learned, right? That's, if you want to interpret that, I can show you, I can write this one is N minus 1. This one right here is N minus P, which is N minus 3. And then this one right here is P minus 1, which is 3 minus 1, so that's 2. That's just to show you that. Okay, now back to what we're thinking about now. What we're really concerned about is what happened here. Let's look at these. So which one's which? So here's our shoe size right here. Look how that changed. That became really small compared to up here. 2.154. It's tiny, and look, it's not significant. Basically, the p-value is pretty high, so that is not significant, that one. What happened to gender? Gender is this one right here. That's really big. And that's very significant. And look, they're not the same as they were in the simple regression. This almost disappeared. This almost disappeared. Okay? And we expected it to, because look, once we included gender, it just about disappeared. It should disappear. There's a slight positive slope here. Okay, so which variables are significant? Only gender. Shoe size is no longer significant. Shoe size hardly matters once gender is included in the model. And let's look at the multiple regression equation, okay, for males and females. So this is the multiple regression equation right here. All I did was I took this right here, and there's the intercept, and that's the slope for gender right here, and that's for shoe size. So this one right here is the intercept. This one's B1, and that's B2. All right. And now it says, what does the above multiple regression equation, how would we interpret this for males and females? What would we do? Well, how would we do that? Well, for males, you have to remember, what are males? They're coded as what? X1 is equal to, you have to look up here, sorry, keep going. to look up here. X1 is 0, the way it was coded for males. So now let's just read this. So what does this say? So this is the number, our predicted number of shoes, Y, is equal to this intercept, 4.255, plus this gender effect, 13.51, but it's times 0, so that doesn't factor in, plus just this tiny bit here that's not really significant, times X2, the number of shoes. So just a tiny bit for each extra pair of shoes. And for females, what does it say? For females, then X1 is equal to 1, so we're doing the same thing. And now we have 4.255, but look at the difference being a female makes. That is really huge. 13.51 times 1. And this, if you add this together, it's 17.765, and this is plus 0.2472 times X2. Now, why didn't we get the same thing? Like, why didn't we get the average for males and the average for females here like we did before? We would have if there really was 0 slope here, but there wasn't. I mean, in real data, there's hardly ever exactly 0 slope. So if you look at it, that's what, otherwise we would have gotten exactly just the average. And it's forcing these two to have the same slope, and they don't exactly have the same slope. See, multiple regression forces them to have the same slope. Let's see what it really looked like. So let's go back to our data and see what it really looks like here. And we're going back to our shoe size, predicting our shoe number, and then we're splitting it. And you see how we don't really have exactly the same. We don't have 0 for either of them. And so when we combine them, we should really, this is the true data, but when we do multiple regression, this is what we get. And that should be exactly the same thing that we got in our on our page. Look down at, isn't it exactly the same thing? It's saying that the males and the females have the same slope, and this is their difference. So it's forcing them to have the same slope. In this case, it's not a terrible thing because they pretty much do. But what about the case where they don't, where the slopes are really different? Then we have to do something, add something called an interaction term. So we can look at a data set that has an interaction, that should have an interaction term, and you can see what happens if, for example, when, let's say that it really did have, in the next data set, we're going to see a data set where there really was a fairly strong effect among females, a negative effect. The bigger their foot, the fewer shoes they had, and for males it wasn't. It was, I think, positive. So what happens then? How can we adjust for different slopes? Then we have to include an interaction term. So maybe we should do that, and then we can do, at the end do an iClicker that's very similar to your homework problem. That's to help make sure you understand how to do the homework that's due Wednesday night. So let's go back to the document camera for a moment. And, whoops. All right, so the next page is the summary here. All right, so this is important, but you can read this on your own. This is what we're addressing right now, that multiple regression forces the same slope for all levels of each variable. So now we're going to address that, and what happens if they don't have the same slope. Like here's another data set where they didn't, and how we can, adding an interaction term allows for different slopes. All right, so let's look at this. This is chapter 13, and it says multiple regression forces the same slope for all levels of each variable. All levels have parallel slopes. When you control for the other variable, and what it means is you have parallel slopes. In the example in chapter 12, that was appropriate since both the male and female slopes were about the same in the individual scatter plots. But what if the slopes aren't the same? What if the relation between shoe size and shoe number differs for males and females? So here's another data set where it did from another year, and we got, when we split, we get different slopes. We see we have this negative effect here. So this is your males, and this is your females. This is like an older data set. I'm sure if you had among my age group, or certainly back years ago, you would definitely have a negative effect among females. I call it the Cinderella effect. I'm surprised it's not there anymore, but people who had big feet didn't want to draw attention to them. It was considered very ugly. So, at least in this country. Shoot, in China, they bound the feet and made them look, so it depends on, so there's somewhat of a Cinderella effect here. That's the story of Cinderella. She had the pretty small feet, and her stepsisters had big, ugly feet. That's like a fairy tale. If you don't, a lot of people aren't from the U.S. here, so you might not have heard of Cinderella. Okay, so this data set is different than the last one, and notice how the slopes are different for males and females. It appears that foot size has no effect on the number of shoes males have. What's the slope? Very small positive. Strongly negative here. But it does have a small negative effect on the number of shoes women have. So when the effect of one variable, shoe size, on Y differs, when it differs depending on the level of the other variable, that's called an interaction effect. Okay? And adding an interaction term to the multiple regression model allows for non-parallel slopes. So it allows us to get the exactly what we get by stratification, the exact equations if we add interaction terms. All right, so let's see how that works. And we'll just do this example and you'll see how that works. All right, so now where's the interaction term? All right, so here we have, oh, sorry, I did something kind of, I shouldn't have, let's just keep, by accident, these got switched around. All right, so let's just make it the way we had it before. So this is gender still, X1 is gender, and X2 is shoe size. Let's keep that, just so we don't get confused. This is gender, and then we have for gender, we have X1, we said 0 is going to be for the men, and 1 for the females. We'll do that the same way. All right, it's a 0, 1 variable. Now, let's just keep it the same color here. So here we have our X1, here we have our X2. And an interaction effect is this, it's a multiplicative effect. You're multiplying X1 times X2. That's what you do when you do an interaction. You're multiplying those two. All right? So we can find the multiple regression equation by combining those two simple stratified regression equations, by combining these two, right here, these two. Don't confuse those stratified regression equations below. That's what we're going to be doing. We're going to be combining two stratified ones. Look, both shoe size, right? These two stratified equations below, each making predictions from the same X2 variable, from the same X variable shoe size. Don't confuse that with the two simple regression equations we saw at the end of the other chapter, which were making predictions from different X1s. One was from gender, and the other one was from shoe size. That's something else, okay? So in this case, we're combining the two stratified simple regression equations, both dealing with this, with shoe size predicting shoe numbers, into two, we're stratifying them into and we're going to combine them into a multiple regression that will give us exactly the same thing as the stratification by including an interaction term. All right, so let's do that. So how are we going to do it? So since x1, I'm changing these. I changed x1's gender. All right, so let's just do this. So the x1 is, we're going to keep, that's the gender, and that's our shoe size. And this is x1 times x2. All right, so how are we going to do this? Now, the best way to do this, I want to combine it into an equation that will give me, when x1 is 0, when x1 is 0, it will give me this one. When x1 is 1, it will give me this one. Okay, that's what I want to do. So what do you need to put in these blanks? All right. Well, when x1 is 0, let's just forget about, that would make this 0 and this 0, right? For males, this is going to drop out and this is going to drop out. So shouldn't we just have put this equation in here? Like put 5.849 in for here, and then 0.0655 there. That way, when x1 equals 0, and it's equal to, when x1 equals 0, I'll get the right equation for males. Does that make sense to everybody? Does it? When x1 is 0, you won't have this, and I'll get that equation. Now I want to get this female equation. So when x1 is 1, when we have x1 is 1, what do I want to get? Well, I want for the intercept, when I put a 1 in here, I want to get that, 29.24, right? I want 29.24, but I have to subtract that one off, right, to get that. Because right now I have 29.24 plus that. So if I do 29.24 minus 0.5849, that's what I want in here. So I want to do, if I add that together, 29.2, isn't that right? I want to get 29.24. When this is a 1, my intercept is going to be this plus that. So I just want that, so I have to subtract that part off. So what I should put in there, let me just do that subtraction. And when I do that subtraction, what did I got? This should be 23.39. That's what I should put in. I'm just saying 5.849 plus this is 29.24, right? Isn't that when x1 is 1? Now what do I want here? I want it to turn out to be, this is a bad way to write, I should have written it like this. I want it to turn out to be -1, that's so confusing, -1.117. That's what I want it to be. But I already have this here, so I got to subtract that off. So when I add those together, I get -1.18255. That looks prettier, doesn't it? So this plus this gives me that. I just made it a little messy, but you get the idea. Any questions on that? Does that make sense to everyone? Okay, so, because why? Because when x1 is 1, when x1 is 1 here, I have, these are both x2, so I want it to be the coefficient in front of x2 there. I want it to add up to that. And so let's see if that's what the program gave us. And when I did it here, and I did the multiple regression here, I get, this is the intercept, right? This is B1, this is B2, B2, and this is what's called B12, the interaction slope. All right? And this one should match up with that. This is what I'm doing. Maybe it would be better if I color code it because it's hard to. So the gender is here. The shoe size is here. And this is gender times shoe size. Okay. And this one matches up to that. This matches up here. And this one matches up to that one. Now, which ones are significant? Let's see which ones are significant. And this one's not significant at all, shoe size. Doesn't matter. Even though it was super, we had a big, strong effect here. Negative 2 point, there's the, it was almost negative 0.4 R, and our slope was negative 2.705, very strong negative. That is not significant. That's p-value of 44.42. We'd see that all the time just by chance. But the gender is very significant. And look how big an effect it is, 23.39, very significant. So that's, remember this is a different data set than the other one we had. And this interaction is also significant. All right. And here, now we have these, we're going to have what? P minus 1, and P is 4. There's 1, 2, 3, 4. So our number of parameters here, the number of parameters, we call them P. Don't get it mixed up with the p-value. The number of parameters is equal to 4. So there's our degrees of freedom is 4 minus 1. And this is, our sample size was 970 here. That's n minus 1. And this is 970 minus 4. All right. So only gender in the interaction term is significant. Now, why don't we, I didn't think I was going to get this far, but, so I don't have homework yet on this for Wednesday. Well, that's fine. But let's just look at the summary, and then let's just do a homework problem to make sure you know how to do it, and I've made it into an iClicker. We can do it together. All right? Similar to your homework. So here, this is the linear models with just the main effects, just look like this. They're called the main effects. But then when you include, see, there's no multiplicative terms here. This is like for k predictor variables. And here, if you have interaction effects, then you have this multiplicative effect. That's the interaction term. And it's added if you think the effect of x1 on y changes depending on the value of x2. All right? It's a multiplicative effect. And here's your example. All right, so now let's go to let me get out your iClickers and let me ask you. Okay. All right, so this scatter plot below shows two groups, this red group and this blue group. And this is this overall green regression line. It's misleading. Look, it's saying overall we have a negative effect, even though there's a strong positive effect. There's this positive effect within each group. Now, what I want you to do, so this is a simple regression. Just this green line is just, y equals some intercept plus some slope. It's wrong. So, I mean, it's confounded. So what we want to do is find a multiple regression equation that is we want to include group membership into a multiple regression equation so that we get the same exact equations that describe the red group and the blue group accurately. And since they have the same exact slope here, we don't need an interaction term. So find the multiple regression equation that gives the same exact lines as the blue and the green lines above. And this is, you have to use this piece of information. Code G equals 0 for the red group. G equals, when it's red, you want this is G equals 0. We're going to include, see there's no G in here, right? There's no G. We're going to make a multiple regression. This has an X, that's one predictor, and it has a G, that's your other predictor. So you have two predictors. So G is either 0 or 1, depending, 0 for red and 1 for blue. And so just figure out which one of these equations will give you the red group when G is equal to 0 and the blue group when G is equal to 1. So just try to see if you can do that and think about it for a minute and then see if you can do that. And again, just participate. Even if you don't think you're right, participate, because this is credit for participation. So I'll end it in a little while, but everybody should vote so you get credit for trying. So why don't I end it at 3 minutes and just meanwhile think about it. But and you can talk with each other and see what you think. All right, so I'm going to end it now. So just here, just vote if you haven't yet. Everybody just vote anything if you haven't yet. Okay, so I'm going to stop it. And let's see what you said. So overwhelmingly D. All right, that's correct. So let's look at that and see why. All right, it's D because you can see that when G equals 0 for the red, you get 5 plus 1 point, you get that. And when G equals 1, you just have the 5 minus the 7. So that gives you that. Okay? Does everybody understand? All right, let's look at the next iClicker then. Okay. Now, it's exactly the same exact question, but I switched the coding. So what if G was equal to 0 for blue and G equals 1 for red? So I just switched that on you, and you want to get those. Now, which one are you going to choose? Oh, sorry, I didn't start it. Thank you. So you should be good on this question. There's questions like this on the homework, so you'll be good on this part if you understand this. Seems like we're doing pretty well, so we can stop it at a minute. Okay, there's a few of you, just a couple more, one more person. Don't you want to get points? There was 98 before, who knows? Okay, you're good? All right, let's stop it. and see what you said this time. Great, it's C is the right answer, and let's look why. And you can see that when G equals 0 for the blue, you get this blue one right here. And then when it's 1, you get 7, when there's a 1 in here, minus 2, which gives you the 5 you need. These all had the same slope, so you didn't have to worry about the interaction term. So then we're going to, I didn't post any homework on interaction terms because I didn't think we'd get to that, but maybe I can open it up, so that would be on Monday's homework. Because I think you probably know how to do it now. All right, so that's it for today, and we finished early.